You're about to watch matter do something it should never do, and yet it does it every time. In 10 minutes, we'll rebuild the double-slit experiment from the ground up, see a single particle paint an interference pattern, and learn why merely knowing which path erases that pattern. No mysticism, just where our everyday logic breaks and quantum logic takes over. Start with a beam of light and a wall with two narrow openings. If light is a wave, the two slits act like two ripples on a pond. Where crest meets crest, the screen beyond gets bright. Where crest meets trough, it gets dark. You get a barcode of bright and dark stripes, an interference pattern. That's fine for waves. But what if we dim the light until the detector clicks one photon at a time? We send single photons. Each photon lands as a tiny dot. Dot by dot, a picture emerges. After minutes, hours, the dots arrange themselves into the same bright dark stripes that waves make. One particle at a time is somehow building a wave's pattern. If you've never seen this before, that's the first crack in classical intuition. Now swap light for electrons, tiny pieces of matter with mass and charge. Fire them one by one through the two slits. On the screen, the same story. Individual hits, wave pattern over time. Matter, like light, is showing interference when you set up the conditions that let possibilities overlap. That sentence, "when possibilities overlap," is the key to the whole experiment. Where does the pattern come from mathematically? A particle heading to the screen has more than one route. In quantum mechanics, each route carries an amplitude, a complex number with a size and a phase. To predict the chance of landing at a point, you add the amplitudes from both slits, then square the result to get a probability. Sometimes the phases help each other, bright. Sometimes they cancel, dark. That add then square rule is the how behind the stripes. So why not just peek and see which slit the particle really took? We can try. Put a tiny detector at one slit that clicks if a particle passes. Now run the experiment again. The screen no longer shows stripes. It shows two broad humps, like a simple sum of two single-slit patterns. The act of acquiring which path information killed the interference. Two myths to clear right here. First, consciousness collapsed the wave function. No. The detector interacting with the particle is enough. A mundane, inanimate device destroys the delicate phasor relation by entangling the particle with extra degrees of freedom. Second, measurement is just disturbance, not quite. You can, in principle, disturb very little and still get which path if the information leaks into the environment. It's not poking, it's information flow. That brings us to decoherence, the practical reason interference vanishes in the macroscopic world. When a quantum system becomes entangled with the environment, air molecules, stray photons, vibrations, the phases that used to add cleanly become scrambled across countless invisible records. From our point of view, the interference terms average away. The pattern you could have seen if everything were isolated gets washed out, not by a mind deciding, but by the world keeping too many copies of the witch path story. There's a wonderfully sneaky version called quantum eraser. First, you mark the paths, say, by giving photons different polarizations at each slit, so interference disappears. Then, after the slits, you mix those polarizations in a way that erases the path mark before detection. If you sort the clicks by how you erased, the interference reappears within those sorted subsets. Did we change the past? No. We changed which subset of data we look at and whether that subset carries enough phase information to show stripes. The order of operations in spacetime remains causal. The math of amplitudes explains the rest. Another twist, close one slit. The pattern becomes a single broad blob. Open the second slit. At some places, the final pattern gets darker than with one slit. You added a path and got fewer hits. That's interference in its purest form. Adding possibilities can subtract probabilities. It's not a paradox, it's the square of sums. Add two arrows pointing in opposite directions and you can get a short arrow. Square the length and you get a small number. What about particles that are definitely lumps, like buckyballs, molecules of 60 carbon atoms? Experiments have launched them through slits and still seen interference. As you go bigger, keeping coherence gets exponentially harder because decoherence lurks everywhere. But the principle holds. Quantum mechanics doesn't stop at some size. We just stop being careful enough to protect phases. Here's a clean way to hold the whole picture. The wave function is a calculator for probabilities, not a mist that spreads through space you can bottle. It evolves smoothly and deterministically by the Schrödinger equation until interaction, entanglement, ties it to other systems. What we call collapse is our switch from a description with many coherent alternatives to one where those alternatives have leaked their telltale phases into the environment. After that leak, interference between them becomes unobservable for all practical purposes. Does the experiment prove reality isn't real? It proves that reality at small scales is built from possibilities whose phases matter. When phases are intact, the world can combine alternatives and produce patterns that no single, definite path could. When phases are recorded by the environment, those combinations disappear and the world looks classical again. The strangeness isn't that particles are indecisive, it's that the rules for adding possibilities differ from the rules for adding certainties. Why should you care beyond the wow? Because this is how modern technology works. Lasers rely on phase-locked light, macroscopic coherence. Quantum dots glow in colors set by wave functions trapped in tiny boxes. Superconducting qubits in quantum computers are engineered double-slit machines in spirit. They maintain coherent alternatives long enough to interfere and give useful answers. Every time you see interference in a device spec, you're seeing double-slit logic made practical. Let's end by returning to the screen. If you let the experiment run long enough with both slits open and know which path leaks, the stripes sharpen. If you add a whisper of gas in the chamber, the pattern softens as random collisions steal phase. If you heat the slits so they glow faintly, thermal photons mark the paths and the pattern fades. Nothing magical, just the world insisting on keeping score. The double slit is famous because it's the smallest lab where reality tells you its full name. Possibilities plus phases plus information. Learn those 3 words, and the weirdness becomes a language you can speak, not a riddle you endure. You don't have to believe in paradoxes. You only have to believe what the screen draws, one click at a time. Part 1 showed the crack in classical intuition. Now let's push it wide open. New setups, bigger particles, delayed choices, and the one rule that keeps all the weirdness sane. You only see interference when alternatives are truly indistinguishable. Begin with a practical question. Why do we always use lasers? Because coherence is the permission slip for interference. Think of each path through the slits as an arrow that carries a phase. If your light source is chaotic, many frequencies, random phases, the arrows don't add up reliably, and the bright dark stripes wash into a blur. A laser gives you long, steady arrows. It extends the coherence length so that path length differences across the slits still let phases talk. Do the experiment with a warm lamp and narrow filters. The pattern is faint and fussy. Do it with a cheap diode laser. Suddenly, the universe enunciates. Now swap the slits for mirrors and beam splitters. The Mach-Zehnder interferometer. It's the double slit in a tidy box. One beam splitter creates two paths. Mirrors steer them. A second beam splitter recombines them into two output ports. With the path lengths matched, one port goes bright, the other dark. Every photon exits the bright port because amplitudes cancel in the dark one. Remove the second beam splitter and the same device becomes a witch path machine. Each detector now tags a path, interference vanishes. Here's the twist. You can decide whether to insert that second beam splitter at the last moment, after the photon has already entered. The statistics still obey whichever choice you finally make. That's Wheeler's delayed choice in a nutshell. It doesn't retro-edit history, it simply reflects what information is available when the amplitudes meet the screen or don't. The rule is causal. The inference we're tempted to make, the photon must have chosen a path earlier, is what needs editing. Tagging paths can be gentler than putting a clicker in a slit. Put a tiny polarizer at each slit so that photons through the upper slit emerge with, say, horizontal polarization and the lower with vertical. You haven't blocked anything, you've marked the paths with distinguishable labels. The stripes are gone because, in principle, someone could learn which path from polarization. Now place a final polarizer before the screen at 45 degrees. That mixes H and V into the same basis and erases which path information. Look at all detections together, still a blur. But if you split the data by how that last polarizer is oriented, or by two complementary orientations in a fancier setup, interference patterns reappear within the sorted subsets, fringes and anti-fringes that add to the washed-out whole. That's the quantum eraser. We didn't change the past. We changed whether the final data preserve or discard the telltale differences that ruin phase addition. Push further with entanglement. Create pairs of photons. Send one, the signal, through the double slit and keep the other, the idler, in a separate lab. Encode which path information on the idler. On the signal screen alone, you see no stripes. But if you later sort the signal hits by how you measured the idler, choosing a basis that erases or reveals path marks, you recover fringes within those conditional subsets. The timing can be arranged so your choice on the idler comes after the signal has already hit the screen. Adelaide choice, quantum eraser. What changes isn't the past. It's the correlation you build between two records. Interference lives or dies on indistinguishability, and entanglement lets you decide which questions your data even make meaningful. If that still feels slippery, anchor it with a trade-off you can feel: visibility versus distinguishability. High contrast fringes, visibility near 1, only happen when which path knowledge, distinguishability, is near 0. As your path tags get stronger, brighter leaks, better markers, the stripes fade. You can dial this continuously by rotating those polarizers at the slits. It's not mystery vapor turning into particles, It's the arithmetic of adding arrows when you know too much about which arrow came from where. Let's go heavier. Interference isn't just for photons and electrons. Neutrons, as bulky and neutral as particles get, interfere in Mach-Zehnder-like crystals. Tilt the apparatus in Earth's gravity and the phase shifts. You literally watch weight change the quantum stripes. At the molecular scale, C60 buckyballs, 60 carbon atoms, have drawn fringes after drifting through nanogratings. Even larger organic molecules have done it with careful source prep and ultra-clean vacuum. The lesson is simple and brutal. The boundary between quantum and classical is not a size limit, it's a coherence budget. Big objects leak phase information to the environment faster. Dust, thermal photons, air molecules, all the invisible tattletales steal just enough path data to kill the pattern before it can build up. Protect the arrows, and even lumps behave like waves. What exactly steals that information? Everything that can, will. A warm slit radiates infrared light that can, in principle, carry away a witch path hint. Residual gas scatters off the particle, leaving a microscopic acoustic memo. You came this way. Vibrations jitter path lengths randomly. The technical art of modern interferometry is not making quantum things. It's muzzling those telltales, cooling, isolating, evacuating, filtering, until options truly overlap. Let's peek under the hood of measurement. In our story so far, detectors click. What happens between unseen and click? The particle's degrees of freedom become entangled with many others, a photodiode's electrons, a lattice's vibrations, eventually a macroscopic voltage on a wire. Decoherence is the spread of phase info into a billion hard-to-reverse channels. In principle, unitary evolution never stops. In practice, interference between macroscopically distinct alternatives becomes unobservable in a microsecond on a warm table. That is enough to live a classical life. No mystic mind is required. Brains come in after the universe has already sent the phase to the shredder. But which interpretation is right, you'll hear. Pilot wave, Bohm, says a real wave guides a real particle through both slits, while the particle takes one path. Many worlds says the full superposition evolves, and what looks like collapse is you becoming entangled with one branch. Copenhagen cautions you to stop asking about underlying stories and focus on preparation and outcomes. Cubism reframes the wave function as an agent's betting book. Here is the useful part. They all reproduce the same stripes when you compute with amplitudes and account for information. The arguments differ on narrative, not on the recipe that makes the screen draw bars. If you want to build things, lasers, qubits, sensors, the recipe and the information rule carry you further than metaphysical wrestling. Let's correct a few famous misreads while we're brave. Observation creates reality. Observation creates records. The world's amplitudes evolve whether or not an eye is present. A camera left in a cave will kill interference the same way a person would, because it entangles and stores witch path data. We influence the past in delayed choice. No. We influence which correlations are visible in the present datasets. The past light cone is safe. Causality hasn't budged. Interference proves particles are conscious. No. Interference proves probabilities are built from complex amplitudes whose phases must agree to add constructively. What about the Afshar experiment you might have seen in comment threads? It claims to show both witch path info and interference at once. The resolution is always the same when you unpack the actual information available in each subset of data. The visibility, distinguishability trade-off holds. Clever optical layouts can make it look as if you got both. Careful accounting shows you didn't. If you want to build an intuition bridge between math and gut, hold on to two pictures. First, arrows. Every allowed path is an arrow. The screen brightness at a point is the squared length of the sum of arrows to that point. When you know which bundle an arrow came from, you don't add it to its rival. You add its intensity separately. Second, records. A record is anything in the world that could, in principle, be consulted to tell paths apart, even if no one will ever read it. The mere existence of a durable correlation turns arrow sums into intensity sums. The rest is vocabulary. Zoom back to tech. Your phone's camera sensor counts photons using avalanche photodiodes operating near the single photon regime. Quantum key distribution sends single photons through interferometers to guarantee eavesdropping would disturb phases. Gravitational wave detectors, LIGO, Virgo, Cagra, use kilometer-scale interferometers so sensitive that they worry about stray thermal photons, mirror vibrations less than a proton's width, and quantum shot noise of light. They inject squeezed light to reshape quantum fluctuations. Again, pure double-slit logic on a cosmic scale. In every case, engineers design around one question: how do we keep phase information where we want it and destroy it where we don't? There's also a human-scale lesson hiding in the math. Adding possibilities can decrease a probability at a specific place. That sounds paradoxical until you remember you're squaring the length of a sum of arrows, not adding raw head counts. In life, we often assume more options can't hurt. Quantum mechanics says sometimes options cancel each other's effectiveness because of how they combine. It's not a moral, it's a metaphor that will keep you honest the next time you think more is automatically better. A neat historical footnote. You can do single electron double slit, even if only one electron is in the apparatus at a time. That kills the old dodge that electrons talk to each other. The interference is self-interference of a single amplitude spread across two roots. Tonomura's classic experiments in the 1980s hammered that point home with patience and exquisite vacuum. Let's revisit the weakest link. Observation without disturbance is possible. If disturbance means momentum kicks, you can make them vanishingly small and still lose fringes, because the cost was never the kick, it was the bookkeeping. When witch path information leaks into any robust degree of freedom, polarization, a phonon, a spin in a crystal, the coherence between paths is gone for all practical purposes. Engineers exploit this mercilessly. They design systems where the only robust record that survives is the one they choose to read. Now for a quick gallery of double slit in the wild. Soap films show interference because light reflecting off the front and back surfaces adds with a phase that depends on thickness. Tilt the film and colors march. Your noise-cancelling headphones interfere sound using anti-phase waves. Holograms store interference patterns that later reconstruct full 3D scenes when you illuminate them. None of these are quantum in the sense of single quanta. All of them are interference. The quantum part enters when you can't consistently tell which microscopic alternative happened, and then the world starts drawing stripes one click at a time. Where does this leave reality? With a cleaner definition. Reality is what the world consistently records. When alternatives share no durable records and remain indistinguishable, they combine as amplitudes and create interference. When alternatives become tied to records, they stop interfering and behave like exclusive cases. The same electron can belong to both categories in different contexts. That's not contradiction, it's context. If you run the lab yourself, 3 knobs decide your fate: source coherence, path symmetry, and environmental isolation. Tweak them, and you can watch the universe drift from classical to quantum and back like a dimmer switch. Open a slit more. The envelope speeds up, the stripes spread. Warm up a mirror. Fringes soften. Pump down the vacuum. Fringes sharpen. You aren't changing the soul of matter. You're changing whether the world can keep a secret. Let's close where we started. A screen quietly painting bars from single impacts. There's no drama in a single click. The drama is in the pattern that emerges when you refuse to peek. That pattern is not a suggestion, it's a measurement, repeated 1,000,000 times. If your picture of reality can't make peace with it, change the picture. The experiment is the teacher. So carry this out of the room. Possibilities have phases. Information chooses whether they add as waves or as mere counts. Decoherence is the universal gossip that kills fragile superpositions. And the double slit is the simplest place the world tells you all of that without apology. You don't need mysticism to be amazed. You only need to watch the screen, protect the phase, and listen to what the clicks say when they sing together.